We will apply this phase slope information to the age-old audio formula time equals 1 over frequency, otherwise known as T equals 1 over F. The 1 in this formula will be replaced with the change in phase over 360, which gives us the number of wavelengths of delay over frequency. So the top part of the formula translates phase shift into wavelengths, whereas the lower part, frequency, is going to give us a span of frequencies over which the phase shift occurs. So we have the range of phase change over the range of frequencies. Let's take this formula and apply it now to an example phase over frequency trace by analyzing the slope. We're going to start with a range from 500 to 1500 Hertz. So here's our values. Frequency high is 1500. The frequency low is 500. Those give us phase values of 540 and 180 respectively. Now you might wonder, how did I get 540? Well, 540 comes from an original phase response that started at 0, wrapped around to 180, then turned itself, to 360, coming over again to 180, which is 540, for a total span of 360 degrees between those 2 points. So for a 1000 Hertz span, we have 360, or 1 wavelength of change. 360 divides out, and you end up with 1 over 1000. It's a negative 1 since it's delay, which translates to 1 millisecond of delay. Let's return to our phase response, but we're going to work in a different frequency range, this time going from 4000 Hertz at the top to 1000 Hertz at the bottom, a span of 3000 Hertz. Following the phase response starting at the 360 degrees, we see it turn, and then turn again, and turn yet another time, for a total of 1440 degrees of phase shift minus the original 360, for a phase difference or phase shift of 1080 degrees. 1080 divided by 360 factors out to be 3, so 3 wavelengths, which you can readily see, over the 3000 Hertz span will divide out to become, once again, 1 millisecond. What's revealed here is the rate of change of the phase spiral. For every 1000 Hertz of change in frequency, there is a phase shift of 360 degrees. We're going to look at one more frequency range to show the fact that it's not required for us to make a complete turn of the phase cycle to find out what the delay is. In this case, we're going to look just at a 90-degree span from 180 degrees to 90 degrees over the frequency range of 450 at the top to 200 at the bottom. This is a change of 90 degrees, or a quarter of a wavelength, over a span of 250 Hertz. This comes down to 0.25 over 250, which is the same as 1 over 1000, 1 millisecond. We're going to look at a series of responses and show the phase spiral unwrapping. We'll start from 0 Hertz, and we can see that by the time we reach 500 Hertz, we've gone 180 degrees. By the time we reach 1 kilohertz, 360. 2 kilohertz yields 720, or 2 wavelengths. And on it goes. For every rise in 1000 Hertz, we change the phase by 360 degrees. The phase response shows an ever-steepening slope. The reason for the increasing slope is the fact that it is a logarithmic display of this linear mechanism of the phase wheel turning at a rate of 360 degrees for every 1000 Hertz. Now we're going to look at another kind of phase response, one that does not have a constant delay over frequency. An example of this in the real world is any loudspeaker ever made. Therefore, this has some very strong practical implications for us. Alright, so let's focus in now on this response, and we're going to take a look, and we're going to call this area here at the about 4 or 5K. We're going to call that T0 because that's the flat part in the phase response. Every place else has a phase angle, and their phase angle is all angled downward, so we know that those are all arriving later than the signal that's up there between 4 and 8 kilohertz. Now we're going to focus in on the range below for the first 180 degrees of phase shift. It takes a frequency at the top of 4K, 4250 exactly, and ranges down to 1250 for a 180 degree change, or half a wavelength, over a 3000 hertz span. This translates to 1/2 of a cycle over 3000, which is 0.17 milliseconds. So we can stake that part out and move on to the next range below that. We've got a area below running from 1250 to about 750, which makes a convenient 360 degree span. By going from the top of the screen to the bottom of the screen, we know we've gone a full cycle. We have to just get the span of frequencies, which is just 500. 1/500 translates to 2 milliseconds. This process now will continue for the next cycle. It has a similar look to it, a 360 degree span, but it occurs in just a 400 hertz frequency span. So it's the same amount of phase change, 360 degrees or one cycle, but in a smaller amount of frequencies. Therefore, it takes more time, in this case 2.5 milliseconds. We're going to do it again now. We're going to take the next round. The picture is quite similar. A similar slope to the phase response, but this is occurring now in the range between 350 Hz and 150 Hz, just a 200 Hz span. One cycle at 200 Hz translates to 5 milliseconds. So you can see that as we go down in frequency, we are stacking up larger and larger amounts of delay, stretching the speaker's time response, in this case over a 5 millisecond range. Let's continue. Now we look at the range from 150 Hz down to 50 Hz. Yet again, another full wavelength of 360 degrees. This time, just a 100 Hz span. It's now stretched to 10 milliseconds. We are reaching the end of our phase spiral journey now, as we reach the bottom range of the speaker. In this case, we don't complete the full cycle. We turn only 300 degrees of phase shift in a span of 23 Hz. The very large time delay of 36 milliseconds shown here is a result of both the loudspeaker's response and the filters that are engaged to protect that loudspeaker. Once again, we will unwrap the phase spiral. This time we'll use 0 milliseconds as our base at the top end. We can see that we've added 0.1 milliseconds, 0.17 there, 2 milliseconds there, 2.5, 5, 10, 36. Even though we're keeping a fairly consistent angle on the slope, we're only achieving that by having more and more delay as we go down in frequency. This speaker has a different response in terms of its time at every frequency below 4 kilohertz. This completes our video presentation. We hope you have found this useful. For more information, consult the book Sound Systems Design and Optimization, available by Focal Press. Thank you for your time. Bye-bye.